Now, having direction and magnitude both is a necessary condition for something to be a vector, but it is not a sufficient condition. Now, that may come as a surprise to many of you, because you probably thought the definition of a vector was that a quantity has both direction and magnitude. It turns out there are certain quantities out there that seem to possess both direction and magnitude, but they are actually not vectors. Okay, and we'll talk about some of those quantities, and I'll show you why they're not vectors. So the thing to remember, especially from this slide, is that just having direction and magnitude is not a sufficient condition for something to be a vector. So, for example, electric current. Okay, electric current seems to have both direction and magnitude, right? If I have a wire, I lay it down like this, I could say there is a 5 ampere of current passing through this wire, and whichever direction I lay this wire in, that will become the direction, right? Road signs, finite rotation, they all seem to have both direction and magnitude, but none of them are vector quantities. And the reason they're not vector quantities is this law. They don't satisfy this law. Okay, so if you take a vector algebra, linear algebra, or abstract algebra class in maybe math department or applied math department, you will learn, if not in one of our ME classes, you will learn that vector quantities need to satisfy one of the 8 axioms. And this is one of the 8 axioms, so I'm not specifying all of them, this is one of them. This says that if you take 2 vector quantities, and notice how we are writing the vector quantities. This is important. We write a symbol and we put an arrow on top. So this is what we call a full arrow, okay? You can also have half arrows, and you will see me sometimes actually drawing arrows as half arrows because I'm in the habit of doing that. So this is a half arrow, and that's also a vector quantity. In your textbook, you might see things written like this, a bar on top. That's also a vector quantity. Some other textbooks may write the same vector quantity in bold, okay? So they'll do bold. Of course, it's hard for us to do bold, so we put an arrow on top, right? So if something is a vector quantity, there should be some visual indication that it is a vector quantity. If you do not show the arrow or a bar on top, it is assumed that you're writing a scalar quantity. And there's a big difference between the two. So if you simply write a plus b equal to b plus a or something like that without an arrow or bar on top, people will think you're writing a scalar equation. And that'll be wrong. Okay, and that's not something that we will tolerate in this department. Okay, so you need to get in the habit of showing the arrows or the bar on top of the symbols for the quantities that are actually vectors. So coming back to this law, right, this is called law of commutativity for addition. Now if you look at this, this may seem like very strange to you, right? Because until now you have probably encountered numbers which you could add in any order and the final result is always the same. So if you take 3, add 5 to it, it doesn't matter which way you write it. 3 plus 5 is always equal to 5 plus 3. Answer is always 8. Right? So if you add to integers, to real numbers, to rational numbers, they don't depend on the order. But it turns out that there are quantities that actually don't satisfy this property. Now, the quantities that don't satisfy this property, even if they have direction and magnitude, will not be called vector. And that's the take-home point. Okay? So quantities that can be called vector should satisfy this law. And this provides the necessary condition for a quantity to be a vector. Apart from having the direction and magnitude, they should satisfy 8 axioms, one of which is this one. And I'm only writing only one of those because you will see that most of the quantities that seem to possess both direction and magnitude don't satisfy this particular axioms. Right? Let's look at an example. So road signs, right? Think about what road signs are. Now this is one kind of road sign. There are other road signs too, like stop sign and all those. We're not talking about those. So a road sign which has maybe an arrow shown to indicate some sort of direction for turning, along with a speed limit. Okay, so we have a right turning arrow and the speed limit is 30. We have a left turning arrow, speed limit is 30. So clearly this particular sign seems to have both direction and magnitude, right? The question is this a vector? Okay, so let's say this is A, this is vector A. Assume that this is a vector, right? This is vector A and this is vector B, right? So you can add vector A with vector B, which in real world would be like taking first a right turn and then taking a left turn at the posted speed limit, yeah? Or you could do B, which is this, and then add A to it, right? So you take the left turn and then you take the right turn at the speed limit. Tell me, will you get to the same destination starting from the same point? You won't, right? So you can easily see that. So if let's say you start somewhere here all right? So you first take the right turn at 30 miles per hour. So that's A. This is A. That's what you're doing. And then we take a left turn. So we get over here, right? So that's B. On the other hand, if I do B first, which is this, so I will start again the same place, and I'll take a left turn, and then I'll take a left turn, and then I'll take a right turn. I get over here, right? So clearly, if you do A plus B, which is not same as B plus A, because your final answer is not same. You're not leading to the same destination, which means that road signs are not vectors. Another example, finite rotations. So what are finite rotations? Well, you could take an object and rotate it, right? Now, you can associate in direction and magnitude with the rotation. So I could take this object and rotate it by 90 degrees, and I could say that I have rotated by 90 degrees about an axis that is perpendicular to the plane of this remote, right? I could say that. So I have clearly specified a direction of rotation and magnitude of rotation, which is the angle of rotation, right? So if finite rotations are vector, they should also satisfy the commutativity property, which is that A plus B should be equal to B plus A. So now to prove that vectors are not, that rotations are not vectors, all I have to do is present an example which shows that A plus B is not equal to B plus A, and I have proved that finite rotations are not vectors. So let's say we have this object, right? And we will attach a reference frame to it. We'll say that this is the x-axis. So this x-axis is in the plane of this block, which says Tinkercad. And y-axis is in the plane too, so it's basically going away from you, and z-axis is perpendicular to the plane. Okay, so it's pointing up, right? So I'm not showing y because y is kind of hidden behind the z, but it's there, right? Okay, so let's say our vector A is rotation about z-axis by 90 degrees, right? So rotation about z-axis by 90 degrees. So if you rotate about z-axis by 90 degrees, and anytime when I say 90 degree or any angle without a sign in front of it, that rotation is assumed to be counterclockwise. So convention is counterclockwise rotations are considered to be positive rotations. Okay? So about z-axis, if you rotate by 90 degrees, what will happen to y? Y that was going this way will be pointing this way, and x will be now that way. Right? So z-axis remains same because you're rotating about z-axis, and that's the configuration. Okay? Then we will consider another rotation, which is B, and that's a rotation about x-axis by 90 degrees. So now what we'll do is we'll do the B, and that essentially would amount to doing A plus B, right? So now the rotation about x-axis, which is pointing that way, 90 degrees, will bring y that way up and z this way, right? And you can do this. When you go home, you could take your book, and then you can attach x, y, z axis to it, imaginary x, y, z axis, and then do these rotations. And you can pick whatever you want, right? It doesn't matter whether you pick z-axis or x-axis, 90 degrees or 45 degrees. This is just an example. Now, let's do the reverse. So we'll do B plus A. So if we do B plus A, this is the final configuration we get to. Right? So if you compare these two, clearly the final configurations are different, which means that A plus B is not equal to B plus A. Right? So that's also telling you that finite rotations, even though they seem to possess both direction and magnitude, are not vector quantity because they don't satisfy this axiom that all vector quantities should satisfy. Right? So I say finite rotations over here because it turns out that infinitesimal rotations, which are very small rotations, do obey this property, right? And now that's something you will learn a little bit in detail when you take dynamics, all right? But for now, at least just remember that finite rotations, which are given by a non-zero or not a very small quantity, are not vectors, okay? Same thing with the electric current. You can think of electric current. You have two wires that connect, okay, at some point, let's say, and they are along the same direction, and the currents are moving in the opposite direction towards a common point. They don't annihilate each other, right? If you have 5 ampere going this way, 5 ampere coming this way, the resultant is 10 ampere. Just because these two wires are pointing towards each other doesn't annihilate the electric current. So that's another reason why electric currents are also not vector quantities.